All right. So I think we'll get started with our next talk. Our next speaker here is David Lattimore. He's after travelling the whole way from Australia to be here, so we really, really appreciate that. His talk is on Can Rust Revolutionise Linking 2. So here you go.
Thank you. For the last year and a half, I've been working full-time on writing a linker in Rust called Wild. So for anyone who doesn't know what a linker is, it's the program that takes the output from the compiler and combines them together into an executable that you can run. And why have I been doing this? Well, I think linkers are cool. I think maybe lots of people don't think that, and maybe me thinking that makes me uncool, but nevertheless, I think linkers are cool. And I'll try and convince you that they're cool. So why are they cool? Well, they write the executables that we run. Unless you're running in an interpreted language, it's a linker's job to make the executable that you run of some sort. They get to decide within reason where everything goes in your executable. So they can lay out things. They can decide where each function is placed, where all the data is placed, within the constraints specified by the program, but they can lay everything out. And when linkers get things wrong, then often things tend to fail spectacularly, although they sometimes can fail in very subtle ways as well, which can be even worse to debug. They also give you an excuse for looking at lots of low-level details. So if you want an excuse to be able to learn assembly language and look at assembly language and learn about relocations and all the other technical things that go into linkers, then they're a great excuse to get your hands dirty with some of those kinds of details. And as software engineers, most of us enjoy optimizing things, but often there's no justification for optimizing things. But linkers are great because people really want linkers to be fast. And so linkers I've found to be a great excuse for playing with optimizations and trying to make things as fast as I can. So the Wild linker is written entirely in Rust. A bunch of the tests are written in C, but the linker itself is written entirely in Rust. It currently only supports Linux, and it is 64-bit only, and supports x86, AArch64, and RISC-V is in progress. I've been using it as my default linker on Linux for the last 6 or so months, and it works pretty well. Most of the time I don't even notice that I'm using it. It just works. It works for Rust code bases tend to be fairly homogeneous, so for most Rust code bases I've found that it seems to work well. With C and C++ code bases, which tend to have a bit more of a mix of unusual flags and compilation options, that they tend to be where you tend to hit oddities. But even those, a lot of those are working as well. The linker itself is very, very multi-threaded for performance reasons. And yeah, most of the commonly used features from linkers on Linux are implemented. But there's quite a long tail of less commonly used features that are not yet implemented. Things that, sort of the 1% and 2% of projects might use, but if you need them, then Wild wouldn't yet be suitable. But if you do want to use Wild and we don't support the features that you need for your project, it's definitely worth filing an issue to ask, because that's how I decide what to work on based on what people need. So the performance of Wild, I'll talk a little bit about the general performance characteristics. So for non-debug builds, Wild is very, very efficient. I put a lot of work into optimizing those. I've also put a bunch of work into optimizing debug builds, but so have the other linkers. And so if you've got lots and lots of debug info, it tends to be more constrained by memory bandwidth. You're just moving around potentially gigabytes of data, and memory bandwidth becomes very much the limiting factor, and it's often performs similarly to LLD and mold. Also, if you have enough cores, like if you have a Threadripper or a Ryzen or something like that, then compute efficiency becomes less of an issue. And as long as your linker is multi-threaded, then memory bandwidth becomes the limiting factor. And so in those kinds of scenarios, mold and Wild tend to perform fairly similarly. However, if you don't have a system like that, like I do all my development on this laptop here, and it's only got 4 cores and 8 threads, and so on it, Wild performs quite well. For ARM development, I've got a Raspberry Pi that I do development on, and so I'll now show you a benchmark for that. So this is, in the blue, we've got LLD, In the orange, we've got mold, and in the green, we've got wild. So this is linking the clang binary. So it's a reasonably large binary, clang. From recollection, it's maybe like 180 megabytes, but I could be misremembering that. I haven't shown GNU-LD here. So GNU-LD is much, much slower than LLD, and if I include that on the chart, then it just messes up the scaling. So I just haven't included it. Usually when I'm benchmarking these days, I don't even bother running GNU-LD. I just compare wild against mold or LLD. In fact, most of the time when I'm benchmarking, I'm comparing wild against itself because I'm looking for regressions or improvements. So that's where we're at with performance. So although the linker, I should have mentioned that my initial motivation for starting the linker was incremental linking, which I haven't yet done, but even without incremental linking, we're already seeing some pretty compelling performance. So I want to make Wild a fun project for people to contribute to. If you'd like to contribute, I'd love to talk to you about that. We've already got a few contributors who are contributing actively to it. There's plenty of challenging issues to work on, lots of deeply technical things that you can get stuck into. But there's also a bunch of less technical things. So if you don't want to tackle any of those more technical issues, there are easier issues. And I try to keep up a bit of a supply of good first issues that I've written up with instructions for how to do those things. It can be challenging at times writing those up, but I try to keep up a bit of a supply of them. And so if you can't find anything that you think is suitable, open a discussion on the repository and just ask for something to work on, or ping me on chat or something like that. So two of the main contributors that have been contributing lately have been Martin Liska and Mateusz, who have both been very actively contributing and helping lots. So I'll talk a little bit about some of the contributions they've been making. So Martin did the debug info support and also the port to AArch64, and is currently working on RISC-V support, which is getting close to being usable, or at least getting close to an initial version. So Mateusz has been getting the Rust compiler test suite to pass with Wild, which it does now pass if you run the tests locally. So there were various weird things we had to fix. So there were a few bugs that uncovered. So that was really good to find those and get them fixed. There are also some weird things that the test suite does. So there's tests that pass these shared objects that are missing headers. I don't know where these shared objects came from. The actual object file itself is checked into the repository as far as I know. And so we needed to make our handling of those objects match what the other linkers do. And there's even one test that uses a linker script. So this is all now passing. We've also just started Google Summer of Code, and we've got a contributor from Kei Akiyama-san from Japan, who is a master's student who is going to be helping automate running of Mold's test suite against Wild, so that we can leverage Mold's test suite to find more issues with Wild and get some of those fixed. So once he's got that working, then the project will move on to investigating the failures and hopefully fixing a few of them. So as I mentioned before, with getting the Rust compiler test suite to pass, that required adding basic linker script support. So we've now got a bunch of the basics. So there's quite a lot of features that can go into linker scripts. A lot of them are fairly obscure, but we do have the basics working now. So you can map input sections to output sections. You can set the location at which sections should be placed in memory, and you can generate symbols relative to sections. So those are sort of some of the core basics that linker scripts need to be able to support, and we support those now. Another thing that I've been looking at recently is linker plugins. So these are necessary if you want to do link time optimization. The linker plugin is a shared object that's provided by the compiler, and it's passed via a flag to the linker. The linker then needs to open that shared object and make calls to it, and then the linker plugin calls back to the linker, and the two communicate, and together they take object files that contain bitcode or something like that and optimize it to produce new object files that then get fed into the link. So as you can imagine, this requires some interesting architectural changes to the way the linker works. So that'll be the main challenge of integrating this, is sort of fitting it into the model of the linker as it currently stands. The API was also, it's very C-like, and it looks like it was designed with a single-threaded linker in mind, and so fitting that into a multi-threaded linker can pose some challenges. So as I mentioned before, one of the original goals for Wild was to make it incremental. So the idea here is, if you make a small edit to your code, it'd be nice if we didn't have to redo all the linking from scratch, which is what most linkers do, and Wild currently does. So the idea is we would just detect what's changed, and suppose you've only edited one function, it'd be nice if we could just patch that function to fix it up, and ideally make linking very, very fast. So I thought I was ready to start on this last December, but we keep on finding other things that have higher priorities. So fixing bugs, implementing various missing features, and trying to mature Wild a bit in terms of what it supports. And I have continued to think about the approach that I want to take with incremental linking. And so one consideration that I've been thinking a bit about is whether to do in memory or on disk. I'd originally planned to do on disk. So the idea of on disk state would be when the linker runs, it writes out a state file, and then when you rerun, it loads that state file up and does the incremental linking, then finishes again. I'm now thinking it may actually be simpler if I just kept the linker in memory while you're not using it. So the idea here would be when you go to relink, it would just connect to the already running linker and tell it to relink the program, which would then already have all the input files loaded except for the new one that's been updated, and it could then just check to see what's changed and update it. I may still eventually do on disk state because that could apply to different use cases, but I think for an initial implementation, in memory is looking pretty promising. Another thing I've been thinking about just in the last couple of weeks is deterministic versus non-deterministic incremental linking. So Wild, when you run it normally, is deterministic. I go to a lot of effort to make sure that the output is deterministic. And I assumed that when I did incremental linking, I would need it to be non-deterministic in that you are patching functions and you don't want to go rewriting lots of stuff, because that's kind of the whole point of incremental linking. And so I assumed that I would make it non-deterministic. However, there's a thesis by Kai Naschinski, sorry for the pronunciation, which talks about deterministic incremental linking, and in fact prototyped something like that with LLD on Windows. I don't think it was ever merged, but they prototyped it and got some interesting results. And so that's now another thing that I'm giving some thought to. Whichever approach I take, the priority will be on reliability and simplicity over always being able to incrementally link. So it'll be okay if we say only incrementally linked 95% of the time, and the other 5% of the time we fall back to a full link. We don't need to absolutely always be able to incrementally link. We'd much rather have something that works reliably and is simple to implement. So once incremental linking is implemented, another thing that I'm excited to have a look at working on is hot code reloading. So the idea here would be that it would build on top of incremental linking, but with various differences. So we definitely wouldn't want to be deterministic in the output here, because we need to leave functions. If there's already a function in a particular location, we need to leave it in that location because it could be currently executing. But the idea is, I guess I should step back a moment. With hot code reloading, the idea is that your program is running and you're changing the code, and those changes are showing up in the running program. So suppose you've got a game or a GUI running, you don't need to shut down the GUI or the game. You can just edit it and see the changes straight away. So yeah, so we need to leave functions where they are because they could be currently executing. Again, I would want to prioritize reliability and simplicity over all kinds of updates being possible. So, you know, if you add a new dependency and you've got a large number of changes, then that's not the kind of use case we're looking at here. We're really looking at editing functions, maybe adding a new function, but not making large numbers of changes and then reloading those. So there may be also other limitations. So I may, for example, require that all functions go via the global offset table, because that would provide easier ways of updating, particularly on RISC architectures like ARM and RISC-V. which both have situations where if you're not going by the global offset table, it takes multiple instructions to reference an address. And if you're running and you update one of those locations but not the other, then that would cause problems. And so we can kind of punt on that issue a bit and just use the global offset table, which is just a table of pointers to things. So that means we can just update those pointers. So I'd like to finish by saying thank you to GoSim for giving me the chance to come here, and also thank you to all of my GitHub sponsors who have helped make it possible for me to work on this kind of thing full time rather than having to go and get a real job. So thank you very much to those people. And does anyone have any questions?
If you have any questions, could you please come to the front of the room?
Hi, I'm just linker stripped standardization. Is it just the sort of thing where GNU LD set the standard and any other big linkers might add options and you just have to support what people use? Or is there a nice place where you can kind of look at the state of linker scripts?
So at least on Linux, GNU LD set the standard. So I imagine LLD just follows the same as what GNU LD does. I haven't looked at linker scripts on other platforms, so I don't know what the story is there.
Okay, so the first thing is a bit of a comment on what you said about the incremental linking having like a daemon running in the background that you connect to keep state in memory. That would also be useful for non-incremental linking, right? Because I think it was Mold. They found that on some operating systems it takes a long time to spawn a process, and starting the linker process and then shutting it down adds a lot of overhead. Is that a use case that you've considered?
Yeah, so certainly the shutting down is an issue, and so in my benchmarks, Mold does take a while to shut down. Both Wild and Mold take a while to shut down, and so both linkers now both fork by default. And so both Mold and Wild, so I got this idea from Mold to fork on startup, and then when you finished linking, the parent process exits and the child process, which actually did the linking work, shuts down in the background.
Yeah, to hide that latency from the user.
Yeah, exactly.
Yeah.
Yep.
And the other thing is, you said that link time optimization linker plugin is very designed with single-threaded linkers in mind. Do you see any potential for that API to be reworked in the future, as now multi-threaded linkers are becoming very popular? Do you think LLVM or something might have a new API standard for multi-threaded linkers for plugins?
I mean, it may be possible to. I'd have to look at the implementer. I haven't looked at the way the linker plugin is implemented in GCC to see what it's like from a threading perspective. It may not be too hard to without changing the API. It may be possible to make the implementation more suitable to multi-threading. Have to see.
Hi. So a lot of you've talked a bit about comparing with Mold, right? In the benchmarks you've used and in the various ideas that you've been inspired by. But you're still beating Mold, and that's really impressive. Can you talk a bit about where, I'm sure that you've looked a bit at the architecture of Mold to understand how that system works and how you can compare it to your architecture. Can you go in detail a bit about where you found ways to beat Mold?
So, believe it or not, I haven't actually looked at Mold. I've tried to avoid looking at any of the other linkers because I didn't want to. I guess I didn't want to worry about licensing, if I'm looking at their source code. And also, I just wanted to come up with my own ideas and I felt like if I looked at the way they'd done things, I might end up just doing it that way rather than thinking about it myself and coming up with my own implementation. I know that Mold is very multi-threaded, and my guess is that they're doing a lot more synchronization than Wild is doing. So Wild does very little by way of synchronization. I try to avoid sort of having lots of mutexes and those kinds of things, and instead just, I rely a lot on scoped threads, and so I've got quite a lot of phases. So rather than say having one phase that computes stuff and then when it needs to compute a shared value, sort of locking on that value and waiting for it to be computed, I would instead split that phase into two phases. So the first phase would work out what needs to be computed, and then the second phase will compute those things, and then maybe a third phase will go on to use those computed things. And that way you've got more phases, but each phase can operate without any sort of locking. It's just a bunch of things that need to be split up. So that's my guess, but I don't actually know.
Yeah, thank you.
You mentioned deterministic builds. I recently had some trouble with GNU LD with getting reproducible build with LTO enabled. So just wondering, do you have, what's your plan for that scenario?
I guess I would hope that the linker plugin would behave deterministically. If the linker plugin is not producing deterministic output, then there's probably nothing the linker can do. I guess it would depend on why it's non-deterministic, like where that non-determinism is coming from. But certainly, I'm not aware of anything in the API that would lead to non-determinism. Yeah.
Okay, thanks.
You may have already sort of answered this in one of the answers to the earlier questions, but I was going to ask about the link time optimizations. Often there is sort of the common approach is to turn off multi-threading in order to allow for better optimization for link time optimizations. Is that just because of the way that the API is written, or are there things that you can do within Wild that can better address those trade-offs that other linkers seem to have to deal with?
So at least in the LTO API that I'm implementing against, it's single-threaded in that you just call a function and the linker plugin does the LTO. So the LTO itself is very single-threaded. I guess going back to the question of the API being multi-threaded, there's probably not much. There's phases where it would be nice to be multi-threaded. The phase where it actually does the bulk of the work, it's hard to see how that would be multi-threaded, because I guess it depends. I suppose you could have an API where it split the work up. It figured out what work needs to be done, and then maybe a bunch of those bits of work could be done from multiple threads. So maybe that could be an option for changing the API to support multiple threading. But yeah, at the moment it is single-threaded.
Thank you.
How can we as Rust developers switch to using Wild for testing?
Yeah, so in the Wild README markdown on the Wild repo, there's instructions for. So you can download releases of Wild. You can install it yourself with cargo install or cargo bin install or those kinds of options, and then you edit your cargo config.toml to say use Clang as the compiler. Use Clang for linking, and then use Wild as the actual linker, and then it just uses it for all Rust development.
Thank you.
Thanks for the talk. Just one question about the code reloading, because the way I usually see this happen is you build a shared library, and then in the program, in the main loop or something like that, you unload the existing one and reload the new one. How are you going to handle this? Or I think you have something else in mind.
Yeah, definitely something else. So the actual the idea would be that your executable code is loaded and it remains loaded. It doesn't get unloaded, and any data that you've got loaded, like any global mutable state, is not being unloaded and reloaded. Like everything stays in memory, and you're just adding extra code into that already executable segment. So it's a bit tricky with executables, because executables on Linux get locked when you're running them, and so you can't edit it while it's running. That limitation doesn't apply to shared objects. So one option is to put all of your code into a shared object, not because you want to reload it, but just because we can edit the shared object while it's running without getting Linux's locking getting in the way. Yeah.
I think it's time for lunch now. We've gone slightly over. But David, thank you very, very much for your talk.
Thank you.